Good morning, students. Today we are going to consider higher order differential equations and a part of general solution known as particular integral with a specific case of polynomial of x. In our previous videos, we considered special case of exponential function as well as trigonometric functions, in particular for sine and cos. Today our focus would be on the third special category of the function, which is known as polynomials. And that also we are considering for polynomials of free variable x. So let us start this technique for higher order differential equations. So if I want to find particular solution for this equation, y double dash plus c1y dash plus c2y equal to rx, where dash indicates the derivative of variable y with respect to x. C1 and C2 are arbitrary constants. R of x is a random variable of x. Here, variable y is dependent variable on free variable x. With this assumption, we can start solving our differential equation. Now, it will be convenient for us to define an operator which is known as capital D. So, it is d raised to n as d by dx whole raised to n. So now everywhere in place of dash, double dash and so on, we can take d square and so on. So I can consider the operator form of given differential equation. Let us consider it by taking this d. So it is d square of y plus c1 times d of y plus c2 times y equal to r of x. Considering the left hand side along with separate value of y as d square plus c1d plus c2 times y equal to rx, we can consider the differential form of this equation as f of dy equal to r of x. This is our first step in all possible solutions of higher order differential equations. Now, as I told you earlier also, that for finding particular integral into the general solution, we have three main methods. There is another method also which is known as general method, but generally with help of these three techniques we can find almost all particular integrals. Methods are direct method, method of undetermined coefficients, method of variation of parameters. Today we are focusing on this part, special functions, and also in that we have seen exponential function, sine and cos. Today we are going to start for polynomials. So how to find particular integral? So for that I am considering again the differential form f of dy equal to r of x, and again consider this y as a particular solution. So it gives you yp as 1 upon f of drx. Yp indicates the particular solution into general solution. And now it depends on this function r of x. As I told you, this r of x can be exponential, sine or cos, polynomial of x, e raised to ax plus b into rx, or x raised to n into rx. We have seen these first two cases, exponential and sine or cos. Today we will consider polynomial of x, and later on in the same video series we are going to cover this two parts, combination 1 and combination 2 also. So let us start this method for polynomials. Suppose we have Rx, means the right hand side of the given differential equation as polynomial of x. So what would be value of yp? Yp will be 1 upon f of the Rx, where Rx is dx. Now in this case, we need to focus on this denominator f of d and try to convert this 1 upon f of d into one of the following form, 1 upon 1 minus t or 1 upon 1 plus t. Here t is any random combination of d. So what I am asking to all of you is, in denominator f of d there will be polynomial of d. Consider the lowest possible term of d. If it is constant number, take that constant number outside the bracket from denominator. or if it is the lowest power of d, take that power of d common from denominator. So it will generate 1. And then you can consider given value of f of d in one of these two possibilities, 1 minus t or 1 plus t, where t is the random combination of t. Then later on you can factorize, or you can take the series expansion of this. This is nothing but the geometric series. So 1 plus t square plus t cube plus t raised to 4 and so on, or 1 minus t plus t square minus t cube and so on. And then it depends on the highest degree of polynomial to consider this power of t. So we are not going to consider infinitely many terms of d. Ultimately it will terminate at a certain level, and that depends upon degree of polynomial. So let us go through examples to understand this technique more specifically. Suppose I have this equation y double dash plus y equal to x squared plus x plus y. So the first step is to consider complementary function. And before that, we need to consider operator form. So operator form of this equation is d square plus 1 y equal to x squared plus x plus y. For complementary function, I am taking auxiliary equation f of b equal to 0. It turns out to be d square plus 1 equal to 0, and that is nothing but m1 m2 to 0 plus or minus I. So value of alpha is 0, value of beta is 1. And then you can take case of complex non-repeated roots, which gives you e raised to alpha x, which is 0, into c1 times cos beta x plus c2 times sin beta x, with beta equal to. So this is nothing but your complementary function. Now let us go for particular integral. Now yt is 1 upon f of d of rx. As I told you, take f of d as 1 plus d square, it is x square plus x plus 1. Now here you can see we already have this value 1. It is d square plus 1, so I am rewriting it as 1 plus d square. So this d square is nothing but my value of t. So now I will expand this whole term 1 upon 1 plus d square as 1 upon 1 plus t, with t equals to d square. So it will be 1 minus t plus t square minus t cube plus t raised to 4 and so on, with t as d square. So it is 1 minus d square plus d square whole square minus d square whole cube plus d square whole raised to 4 minus and so on up to infinity on x square plus x plus 1. Now we need to be very careful at this stage. How many terms we should consider out of this infinitely many terms of t? It depends on this polynomial. As we know that this d indicates derivative, so d square indicates second order derivative. D raised to 4, this term indicates fourth order derivative. This term indicates sixth order derivative. So logically, how many terms we should consider? If we have x square plus x plus 1, the highest order of this polynomial is 2. So if I take fourth order derivative of this equation, then obviously it is going to be 0. And this simply means that we need to consider values of d only up to power 2 or less than 2. So I will identify terms out of this infinitely many terms for which the power of d is 2 or less than 2. Rest of the values are not important as they are going to be 0. So there is only one term which is with power 2 or less than 2, and that is d square. From this point, d raised to 4, d raised to 6, d raised to 8, all values are going to be 0. So I am taking 1 minus d square only on this polynomial, and then I am multiplying this whole polynomial with 1, this whole polynomial with d square. So it gives me x square plus x plus 1. Then I am taking derivative of this, so it will give me 2x plus 1. Then again second derivative, as it is d square, so it gives me minus 2. Now simplifying this will give me dx square plus x minus 1, and this is nothing but your particular integral. I would ask you to pause at this stage, go through this solution, check step by step. And if you have any problem, you just rewind this video for some time and again you should check what is happening in this solution. There are three main steps. The first step is to convert 1 upon f of d into 1 upon 1 minus t or 1 upon 1 plus t. Second important step is to consider the finitely many terms out of that expansion of 1 upon 1 minus t or 1 upon 1 plus t. And the third stage is finding the derivatives. And so, for particular integral answer is x square plus x minus 1. And then taking yc and yp combinedly will result into c1 cos x plus c2 sin x plus x square plus x minus 1. This is how you can find general solution in case of polynomials as a special function on right hand side. Let us consider second example. Suppose you have y double dash plus 2y dash plus y equals to x square. In this case, operator form is d square plus 2d plus 1y equals to x cube, and auxiliary equation for complementary function would be f of d equals to 0, which gives you d square plus 2d plus 1 equal to 0, and it is nothing but d plus 1 whole square equals to 0, and which gives you two roots m1 equal to m2 equal to minus 1. And so I am taking the repeated real roots. So it gives me c1 plus c2x into e raised to minus x. This is complementary function. Now let us consider particular integral. So for particular integral, I am taking yt as 1 upon f of d of rx. Now here you can see this 1 upon d square plus 2d plus 1 into x cube. So here already I have that lowest degree term 1. So I am rewriting it as 1 plus d square plus 2d. So this is value of t in my case, and I am taking expansion of 1 upon 1 plus t. So it is 1 minus t plus t square minus t cube and so on. So here value of t is d square plus 2d. So expanding this with help of our formula of 1 upon 1 plus t. Now here you can see the polynomial is only single term x cube, and then I need to focus on this power, which is 3. So I will figure out how many terms in this expansion will be with minimum value 3. So out of this first term, it is constant. Here it is d square and 2d, both are less than or equal to 3, so I need to consider both of this. In this, if I expand, I will get d raised to 4 plus 4 times d square into d, means it will give me d cube. So the first term is d raised to 4, so I should avoid it. So I am taking the middle term. It is 4 times d square into d, so 4d cube. Last term would be 4d square.